In this video, we're going to discuss the inverse of a matrix, and specifically we're going to see how to calculate the inverse of a matrix. A couple of definitions from our previous video that might come in handy. First thing we can talk about is the idea of the identity matrix. So we'll write this I, and if we're talking about 2 by 2 matrices, then the identity matrix looks like 1, 0, 0, 1. Or if we were talking about 3 by 3 matrices, then I would look like this. It would have ones along the diagonal and zeros everywhere else. So both of those are examples of the identity matrix, just depending on whether we're talking about 2 by 2 or 3 by 3 matrices. Now the main idea that we want to recap here is the idea of the inverse of a matrix. So if we take a matrix A, we write the inverse of A as a to the negative 1. And the main property that the inverse of A has is that when you take the inverse of A and you multiply it by A, you get the identity matrix. So you can think of a bit of a parallel here with real numbers. You could say if you take something like 7 to the negative 1 and you multiply it by 7, you get the number 1. Multiplying by 7 to the negative 1, in a sense, undoes the action of multiplying by 7, and it gives you back the real number 1. So in a similar way, the inverse of A undoes whatever operation A does and gives you back the identity matrix. So what we're going to be focusing on in this video is the inverse of A, or we sometimes call it A inverse. We're going to see how to calculate that for 2 by 2 and 3 by 3 matrices. So let's start with 2 by 2 matrices. Let's say someone gives us a 2 by 2 matrix, we'll call it A, and let's say in symbols it looks like A, B, C, D. Then we need to define what's called the determinant of the matrix A. The determinant is just a number. So in symbols, we're going to write that as det A. And the way you actually calculate it, you multiply the two numbers on the main diagonal, so A times D, and then you go minus B times C. So these guys minus the product of these guys. So let's call that a definition. And now that we've got that definition down, we can write down a formula for the inverse of a 2 by 2 matrix. So A inverse is going to look like 1 over the determinant of A times the following matrix. So let's pay attention to what's happening inside the matrix. The entries on the diagonal have reversed. So we've just swapped the A and the D. And then the entries on the off diagonal have changed their signs. So that's our formula for A inverse, 1 over the determinant of A times this modified 2 by 2 matrix. And a couple of comments about this before we jump into some examples. So first comment is that if the determinant of A is equal to 0, then A inverse does not exist. If the determinant of A is equal to 0, then the matrix A has no inverse. And that makes sense based on our formula because it would not make sense to go 1 divided by 0. Second comment is that this formula only works for 2 by 2 matrices. We will see a second method a bit later in this video for how we find inverses for 3 by 3 and bigger matrices. So the problem is to find A inverse, and in part A, matrix A looks like 9, 6, 2, 1. So first thing we're going to do is calculate the determinant of A. So the way you do that, multiply the diagonal numbers together, so 9 times 1, and then subtract off the product of the backwards diagonal. So minus 6 times 2. So you're sort of making this X pattern where you multiply these guys and then you subtract off the product of these guys. So 9 minus 12, that would be negative 3. All right, now that we've got that number, we can write down the formula for A inverse. So we're going to go 1 over negative 3 times a certain modified matrix. So what we're going to do is swap the entries that are on the diagonal. So the main diagonal is the diagonal that runs from the top left to the bottom right. So get 1 and 9 on the diagonal, and then on the off diagonal, the signs are going to change. So negative 6, negative 2. So you could leave your answer like this, or what you might prefer to do is just multiply each entry in the matrix by 1 over negative 3, because we know that a number out in front of a matrix just multiplies with each entry in that matrix. So if you want, you could clean this up and you could say this would be minus 1/3, positive 2, positive 2/3, and negative 3. Now, since this is our first example of using this formula, what we might want to do is just check that this works. So this is completely optional, but just to convince you that the process works. Remember, the whole point of the inverse matrix is that it's going to multiply with your original matrix to give you back the identity matrix. So you can just confirm that when you take this minus 1/3 to 2/3 minus 3 and multiply it with our original matrix, which was 9, 6, 2, 1, let's confirm that we really do get this identity matrix that has ones along that main diagonal and zeros everywhere else. So let's confirm that. So this is a little flashback to matrix multiplication. You would circle the rows of your first matrix, columns of your second matrix, and let's do some dot products. So if we take the dot product of this guy with that guy, yep, we get 1. This guy with that guy, yes, we do get 0. So the top row looks good. And then for the bottom row, so we're doing dot product of these two. Yep, that gives us 0. And then dot product of these two. Yes, that gives us 1. So yes, we've confirmed that we do really get the identity matrix. And so our formula does work. Let's try a part B. Again, the problem is to find A inverse. So first thing we would do here is calculate the determinant of A. So for the determinant, multiply the entries on the main diagonal, so 1 times 4, and subtract off the backwards product, the 2 times 2. And that gives us 0. All right, so it doesn't make sense to divide by 0. Remember, when your determinant is 0, that's an indication that A inverse does not exist. So that's all we have to say there. So now we know how to find the inverse for a 2 by 2 matrix. The other problem we have to tackle is finding the inverse for a 3 by 3 or potentially 4 by 4 or bigger matrix. So we're going to look at what's called the Gauss-Jordan method for finding A inverse. How the process works is you write down your matrix A, and beside that you write down the identity matrix. And then through a series of steps, we're going to turn this matrix into a matrix that has the identity matrix on the left. And what will be popping out on the right is A inverse. So as we go through this sequence of steps here, basically what we're doing is we're undoing A. So A is going to turn into the identity matrix. And as we undo A, what we're building up on the right side is the matrix that undoes A. The matrix that undoes A is A inverse. So I would say the tricky part of this process is just figuring out which operations are legal. There are 3 sorts of operations that we're allowed to do. So first thing we can do is we can swap 2 rows in the matrix. We can multiply or divide any row by any non-zero number. So you can multiply a row by 2, or you can divide a row by 3. And then there's a third type of operation that we're going to do. And I'm just going to describe this one a little differently than it's written in the notes, just to make this a little bit more intuitive. So what you're allowed to do is you can take the current row that you're on and replace it with your current row plus or minus some number times the pivot row. So we'll talk, when we do an actual example in a moment, we'll talk about what the pivot row is and what this operation would actually look like. But for now, let's just keep in mind, there are 3 types of legal operations that we're going to do. So a couple of comments to keep in mind before we go into an example. First thing is that if we create a row of zeros on the left, then that's an indication that A inverse does not exist. I think I'll do a specific example just to point out that scenario. And the second comment here is that this process works not only for 2 by 2 matrices, but for 3 by 3, 4 by 4, and bigger matrices. Now, we already have a fast way of calculating the inverse for a 2 by 2. So I think using this process for a 2 by 2 matrix would be overkill. We're actually going to concentrate on the situation of 3 by 3 matrices. So we're going to do 3 examples of finding A inverse for a 3 by 3 matrix. So let's jump into our first example. So first thing we're going to do is we're going to write down our matrix A, and beside that, we're going to write down the identity matrix. So that's matrix A exactly as it was given to us, and beside that, the identity matrix. So that's got ones along the main diagonal from the top left to the bottom right, and it's got zeros in all the other positions. So what we want to do is turn this left side into the identity matrix using the 3 legal row operations that we just talked about. So I'm going to give us a bit of guidance here as to in which order we want to perform these operations. So first thing we want to do is we want to get a 1 in the upper left-hand corner, so in this position here. And we're going to call this one the pivot. Okay, so anytime you're trying to get a 1, the process that you want to do is just divide the appropriate row through by something. So we're going to take row 1 and we're going to divide it by 2. So all the way across row 1, we're going to divide by 2. Dividing each number, we would have 1, 5, 1, and then continue on the right side as well, 1/2, 0, 0. Okay, and everything else in the matrix can just be recopied. Nothing else is changing at this point. So I usually get in the habit of circling this 1 or this pivot once we've got it, because we're then going to use it to clean up the rest of the first column. So after you get a 1, what you want to do is get zeros in the rest of that column. So if we look at that first column, the number that we're now trying to clean up is this 2. We want to turn this 2 into a 0. So this is where we're going to do the operation that looks like current row plus or minus some number times our pivot row. Okay, so let's make sense of this. So current row is just the row that has the number in it that you're trying to get rid of. That means our current row is row 3. Our pivot row is the row that has the 1 in it. So the pivot row is row 1. So the correct operation that we need to do is row 3 minus 2 times row 1. So why is it minus 2? Well, it's because it's a positive 2 that we're trying to eliminate. So if you imagine applying this operation, row 3 minus 2 times row 1, you go 2 minus 2 times 1 would give us 0. So row 3 minus 2 row 1 is exactly the correct operation to perform to get a 0 in this position. So we'll do lots of practice with this, but in general, anytime you're trying to get a 0, think about going current row plus or minus some number times the pivot row, and the correct number to use is just the negative of whatever number you're trying to eliminate. So let's try applying this operation all the way across here. We're going to go row 3 minus 2 times row 1. So we go 2 minus 2 times 1 is 0. 14 minus 2 times 5 is 4. 2 minus 2 times 1, 0. 0 minus 2 times a half is negative 1. 0 minus 2 times 0 is 0. And then 1 minus 2 times 0 is 1. So that gives us our bottom row. Nothing else is going to be changing at this point, so I'll just recopy everything. So we now consider the first column to be cleaned up, because remember what we're trying to do is build the identity matrix on the left. So you want to ultimately have 1s along the main diagonal, and then you want to have 0s in all the other positions. So we're making some progress, and we just do this one column at a time. So now that the first column is cleaned up, we're going to move from our previous pivot. We're going to move down and to the right, and this is going to be our new pivot. So we now want to create a 1 in that position. So I'll write down what we're doing. We're going to get a 1 on the diagonal. Again, we call that the pivot. And let's think about what operation is going to be required. So anytime you're trying to get a 1, it's just a matter of dividing a row through by the appropriate number. So if we take row 2 and we divide it by 4, that'll work perfectly. So dividing all the way through, 0, 1, 1/4, 0, 1/4, 0. And nothing else is going to be changing at this point, so we'll just recopy everything else from our previous matrix. And I usually get in the habit of just circling that pivot, because then we're going to use it to get zeros in our next step. We're going to get zeros in the rest of column 2. So this is where we're going to practice that more tricky operation where we go current row plus or minus some multiple of our pivot row. So what we're going to do is we're going to try to get rid of the 5 and the 4 at the same time. So you can get a couple of zeros within the same step. It just saves you from having to recopy your matrix over and over again. So to get rid of the 5, you go row 1 minus 5 row 2. So row 1 is our current row. Our pivot is in row 2. So you can see that 1 is circled there. So that's what's telling us row 2 is our pivot row. Since it's a positive 5 that we're trying to eliminate, we're going to go row 1 minus 5 row 2. So at the same time, we're going to try to get rid of the 4 that's in the bottom row. And the correct operation would be row 3 minus 4 row 2. Again, the pattern is that you go current row, so whatever row your number is in, and then plus or minus a multiple of your pivot row. If it's a positive 4 that we're trying to eliminate, then it's minus 4 times the pivot row that we want to do. So let's try this operation row 1 minus 5 row 2. So we're going to go 1 minus 5 times 0 is 1. 5 minus 5 times 1 is going to give us 0. And then 1 minus 5 times 1/4. Okay, if you want to do any just kind of side work, you can go 1 minus 5 times 1/4, and you could say, okay, that's like 4/4 minus 5/4. That would give us minus 1/4. So that's how we get this entry here. And then we still continue the same operation on the right side of the matrix. So we're going half minus 5 times 0. That's going to be a half. 0 minus 5 times 1/4. That'll just be minus 5/4. And then we get 0 in the last position. Okay, now the middle row is not changing, so I'm just going to recopy everything there. And then we can work on our bottom row. So for the bottom row, we're doing the operation row 3 minus 4 row 2. So we're doing this minus 4 times that, 0. This minus 4 times that, 0. 0 minus 4 times 1/4, that's a negative 1. And just continuing that all the way across, we'd have negative 1, and 1. So let's appreciate how much progress we've made here. The first 2 columns are now completely cleaned up. So we've just done this process of getting a 1 and then getting zeros in the rest of the column. Then we got our second pivot, got zeros in the rest of that second column. So we know that we've only got 2 more steps to go. We're going to create a pivot in this bottom right-hand corner, and then we're going to clean up the rest of that column, and then we'll be done. So the process of getting the pivot, or getting the 1, is just the process of dividing the appropriate row by the appropriate number. So we would want to take row 3 and divide by negative 1. Okay, dividing by negative 1 is just like doing a sign change. So we're going to do that all the way across, and we'd have 0, 0, 1, and then 1, 1, negative 1 for that bottom row. And here we go, one more step to finish the problem. So our goal is to get the identity matrix on this left side here. And so what we need to do is get zeros in column 3. We want to get rid of that minus 1/4. Let's think about what row it's in. It's row 1. Let's think about where our pivot is. Pivot is in row 3. Okay, and it's a minus 1/4 that we want to eliminate, so we need to go plus 1/4 times our pivot row. So again, the reason that works is because then we'll be going minus 1/4 plus 1/4 times 1. So that's just the perfect operation to create a 0. The other thing we need to get rid of is this positive 1/4 that we're seeing in row 2. So we'll go row 2 minus 1/4 times our pivot row. And then once we've completed that, we will have our identity matrix on the left side. So let's try it. We'll start with doing row 1 plus 1/4 row 3. So that's going to give us 1, 0, 0. And then just a little bit of algebra on the right side. So we're going to go half plus 1/4 times 1. Okay, well, half plus 1/4, if we think about how many quarters that is, 2 quarters plus another quarter is going to give us 3 quarters. We have to go minus 5/4 plus 1/4 times 1. So that's going to give us a negative 1. And then 0 plus 1/4 times negative 1. That's going to give us minus 1/4. So that's our top row figured out. And then middle row, the operation we're going to do is row 2 minus 1/4 times row 3. So that's going to give us 0, 1, 0. And then continuing that operation, 0 minus 1/4 times 1, it's going to give us minus 1/4. 1/4 minus 1/4 times 1, it's going to give us 0. And then 0 minus a quarter times negative 1 is going to give us positive 1/4. Okay, and then bottom row just gets recopied and we are done. So notice that we've now got the identity matrix on the left side, and what that confirms for us is that this matrix sitting on the right side must be A inverse. The problem was to find A inverse, so we can just put a circle around that and we can say this is A inverse and we are done. So in our next section, in our next video, we're going to see all about how we use A inverse to solve systems. But for now, we're just focused on the algebra of actually finding the inverse matrix. So that was our first example of finding the inverse of a 3x3 matrix. And we're going to do 2 more examples like that just to practice the concept. So we are going to find A inverse for the following 3x3 matrix. So let's remember how this process works. We're going to write down our matrix A on the left, and beside that, we're going to write down our identity matrix. So we'll just copy 1, 1, 6, 0, 2, 3, 2, 2, 12. And beside that, the identity matrix has 1s along the main diagonal and 0s everywhere else. So our goal is, over the course of a few steps, to turn this left side into the identity matrix, and whatever we have on the right side will then be A inverse, which is what we're looking for. So let's remember our sequence of steps. The first thing we want to do is get a 1 in the upper left position, and that 1 is usually called the pivot. That's already done for us. So that saves us a whole step of work. And then once we've got that, we want to get 0s in the rest of that column. All right, so looking at our matrix then, it's just this 2 here that needs to become a 0. So when you're trying to get a 0, the operation you want to do is current row plus or minus some number times your pivot row. So if you look at the row that the 2 is in, it's row 3. And if you look at your pivot row, meaning the row that has the 1 in it, that's row 1. And then what number do we need to use? Well, just the negative of whatever number you're trying to eliminate. So if it's a positive 2 you're trying to eliminate, you want to go minus 2 times your pivot row. And that's just the perfect operation to create a 0, because then we'll be going 2 minus 2 times 1 to create our 0 there. So let's try applying this operation, row 3 minus 2, row 1, all the way across the matrix. So we go 2 minus 2 is 0, 2 minus 2 is 0, 12 minus 2 times 6 is 0. And I'm just going to stop there. So let's flash back to one of our comments that we made when we were first describing this process. So let's focus in on this first note after we describe this process. So just looking down here. The note said, if we create a row of 0s, then A inverse does not exist. So here's our problem, and notice that we have a row of 0s on the left side. Once we see that row of 0s, that tells us that we can't make the identity matrix. So no matter what sequence of steps we go through, there's nothing we can divide through by. There's no swapping of rows, there's no addition of rows that will help us. So this row of 0s tells us that we can't make the identity matrix, and what that means is that A inverse does not exist. So as soon as you see a row of 0s coming up on the left side, you stop the process and you say, okay, whatever matrix I started with, it simply does not have an inverse. So we're going to find A inverse for the following 3x3 matrix and just get a little bit more practice with this Gauss-Jordan method of finding the inverse. So what we're going to do is write down our matrix A, and beside that write down the identity matrix. So we'll just recopy 5, 6, 7, 1, 1, 1, 1, 0, 1, and then beside that our identity matrix has 1s along the main diagonal from the top left to the bottom right, and it's got 0s in all the other positions. Our first task is to get a 1, which we're going to call the pivot. So we're going to get a 1 in the upper left position. So normally the way we would get a 1 is we would divide a row through by something. So we could take row 1 and divide it through by 5. But if we do that, we're going to get a lot of fractions. There's actually a third operation that we haven't used yet that can help us. We are allowed to swap rows. So we can just change row 1 and row 3, meaning bring the entire row 3 up to the top. So we'd have 101, 001, and then bring the entire row 1 into the bottom. So 5, 6, 7, 1, 0, 0 goes into the bottom. And then we'll just keep our middle row the same. So this swapping of rows works really well if you've got a 1 somewhere else in the column. Great, so now that we've got our pivot, we can then do the process of getting zeros in the rest of that column. So for the 1, we're going to go row 2 minus row 1, and to get rid of the 5, row 3 minus 5, row 1. So the pattern is that you're going your current row plus or minus some number times your pivot row. Again, the number that you're choosing here is just the negative of whatever number you're trying to eliminate. So if it's a 1 that we're trying to eliminate, we're going to go row 2 minus row 1. If it's a 5 we're trying to eliminate, we're going to go row 3 minus 5, row 1. So let's try both of those operations. Top row is just staying the same, so I will recopy that. And let's focus on going row 2 minus row 1. So we'll go 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. And then just working our way across 0, 1, minus 1. Okay, now let's try the operation where we go row 3 minus 5, row 1. So that's going to be 0, 6, 2, 1, 0, negative 5. And we've now got that first column all cleaned up. So that looks good. Now let's think about where we are for column 2. So normally we would say we would want to get a 1, but just fluke up the numbers. That middle position already comes out to 1. Remember, what we're trying to achieve is getting 1s along the main diagonal here. So our next pivot is already there for us. Don't have to worry about that. And so what we're going to be focused on then is getting zeros in the rest of column 2. So if we check out column 2, we've already got a 0 in one of the positions. That's great. So it's just the 6 that we're going to need to work on. The way we're going to get rid of that 6, we're going to go row 3 minus 6 times row 2. Again, we're following this pattern of going current row plus or minus some number times our pivot row. Now that we're in column 2, our pivot row is actually row 2. So you can just imagine if you go row 3 minus 6 times row 2, that's going to be perfect for turning that 6 into a 0. So let's try that operation, row 3 minus 6, row 2, all the way across our matrix. We're going to have 0, 0, 2, and then continuing on the right side, 1, negative 6, and then for this one we're going to have negative 5 plus 6 gives us 1. And our top 2 rows of our matrix can just get recopied. Great, so now the first 2 columns are cleaned up. The next thing we need to do is move into column 3. And remember, it's always a pattern of getting a 1 and then getting zeros in the other positions. So we want to create a 1 in that bottom right position, and we'll do that just by taking row 3 divided by 2. So we'll get 0, 0, 1, half minus 3, and a half. And we'll just recopy all the other entries in the matrix so that we're ready for our very last step. So if you like, you can circle that pivot, and then we can get zeros in the rest of column 3. So it's just this 1 in the top right corner here that we need to get rid of. We're going to go row 1 minus row 3, just following the pattern of going current row plus or minus some number times our pivot row. And since it's a positive 1 that we're trying to eliminate, it's minus 1 times our pivot row. So let's do that. Row 1 minus row 3 is going to give us 1, 0, 0. And then doing that same operation on the right side, we're going to go 0 minus a half. It's negative a half. 0 minus a negative 3 is a plus 3. And 1 minus a half gives us a half. Everything else in the matrix just gets recopied. And we have finally built the identity matrix on the left side. So that's what tells us whatever's sitting on the right side must be A inverse. So to finish the problem then, we just circle this matrix that we got on the right side and we say, there we go. there's A inverse. So quick recap of what we did in this video. We figured out how to calculate the inverse of a matrix. If your matrix A is 2 by 2, I would say use the formula to find A inverse. And if your matrix is 3 by 3, then you want to use this Gauss-Jordan process. Let's just call that row operations. Use row operations to find A inverse. So for 3 by 3, 4 by 4, 5 by 5, etc., bigger matrices, we use this process of row operations. So in our next video, we'll see all about what we're going to use the inverse matrix for. So thanks for watching our video on calculating the inverse of a matrix.